Welcome to today's lecture on system characterized by a differential equation using Fourier transform. In this lecture, we will study systems characterized by differential equation and analyze them using the Fourier transform. This concept forms the foundation for understanding continuous time LTI systems. First, let us understand what frequency response means. The frequency response of a system tells us how the system modifies different frequency components of an input signal. That is, mathematically, it is defined as capital H of j omega equal to y of j omega divided by x of j omega, where x of j omega Fourier transform of input, y of j omega Fourier transform of output. If we know the frequency response, we can completely understand the system behavior in the frequency domain. Solving differential equation directly in the time domain can be difficult. So, the Fourier transform simplifies analysis by converting differentiation into multiplication by j omega, convolution into multiplication. Hence, the Fourier transform is widely used for system analysis and frequency response determination. In this slide, we can represent general system differential equation. A continuous time LTI system is generally described by linear constant coefficient differential equation. Linear constant coefficient differential equation. The output and its derivative appears on the left side. The output and derivative, that is d by dtn, that is named as derivatives, appear on left side, and the input here represented as x of t, and its derivatives appear on right side. This equation completely describes the system in the time domain. Now we apply Fourier transform on both sides. Before that, the important key Fourier transform property is here represented as f of d power n into x of t divided by dt n. That is equal to, represented in the form of j omega. Already we discussed this concept. That is here our differentiation converted into multiplication by j omega. That is, using this property, we can simplify the differential equation using Fourier transform. This signal property converts the entire differential equation into an algebraic equation. This is the algebraic equation. This is the differential equation that is converted into an algebraic equation. Using this property we can solve the LTI system. Now we apply the Fourier transform to both sides of the differential equation. This is the overall concept of our Fourier analysis. There is a n into j omega power n plus a n minus 1 into j omega power n minus 1 plus up to, we can represent it a naught into, we can take here capital Y of j omega, that is equal to here bm into j omega power m plus up to represented as into coefficient represented as b naught into common term here represented input term is x of, this capital X of j omega. From this equation, after applying Fourier transform in this equation, this is the our time variant system can be represented by differential equation. When we applying the Fourier property, Fourier transform property here, using this property, we can convert it into the algebraic representation of our given system. From this system, we have to find capital H of j omega equal to capital Y of j omega divided by capital X of j omega. This expression is called the frequency response of the system. Let us now understand this concept clearly with an example. Consider a continuous time LTI system described by the differential equation, that is dy of t by dt plus 3y of t equal to x of t. The input to the system is x of t equal to e power minus 4t into u of t. Here assume all signals are 0 for t less than 0. This is one example problem. From this problem, we can understand the concept of differential equation using Fourier transform logic. So first, we take applying Fourier transform to each term using differentiation property. Already we discussed the differentiation property. From this property, apply that concept on our given equation. Our given equation is here. This system is here dy of t by dt. Applying here our differentiation property, then also apply in this term also we can apply the differentiation property, then this terms also. So after applying the our property differentiation property, we can get our equation like this, that is j omega into y capital Y of j omega plus 3 into capital Y of j omega equal to capital X of j omega. From this, we have to find output response or frequency response. First, we can find solve the capital Y of j omega. That is, the already we discussed all the left side we has only output representation, and the right hand side we has only the input representation of our system. So from this we can take common term, that is common term means in this equation here can take y of j omega in the common term. So after taking this common term y of j omega into j omega plus 3, j omega plus 3, that is equal to capital X of j omega. So from this, what is the frequency response equation? That is capital H of j omega, j omega equal to, that is y of j omega, y of j omega divided by capital X of j omega, capital X of j omega. This is the frequency response of given system. From this equation, we can find the frequency response value, that is h of j omega equal to y of j omega divided by x of j omega. So one we can take this x of j omega comes into the left hand side. That is when once comes into left hand side, this comes under our denominator term, that is capital X of j, capital X of j omega. After this, we can get our answer like this, 1 divided by j omega plus 3. This is the frequency response of our given system. Frequency response of our given system. After solving our frequency response, we can solve the response of, that is y output response capital Y of, from the capital Y of j omega we can find the small y of n, that is output response of a given system. That is after this concept, that is we can take, that is the left hand side only we keep our notation capital Y of j omega, that is equal to capital X of j omega divided by j omega plus 3. Once we can find the capital Y of j omega, we can compute capital X of j omega. Already the given input signal value equal to x of t equal to e power minus 4t into u of t. After applying the standard CTFT result, already we know that Once we are applying Fourier transform logic in this given signal, that is f of e power minus at into u of t equal to 1 divided by a plus j omega. Instead, in this given sum, instead a, we have minus 4. That is, instead a we can have 4 only, not minus 4. So that is a equal to 4. So using the standard CTFT result, we can solve this answer. We can compute capital X of j omega, that is equal to 1 divided by 4 plus j omega. Instead a we can substitute 4. From this standard result we can solve this answer, that is capital X of j omega. After that, we can find small y of t using inverse Fourier transform. So already we found the value of frequency response, that is h of capital H of j omega. After that, we can find we found capital Y of j omega, then capital X of j omega. After from this concept, we can find small, that is output response of our given system. So from this one, let us discuss step by step. That is, substitute capital X of j omega in our capital Y of j omega equation. That is, in this here you can substitute X of j omega value. So that is equal to 1 divided by j omega plus 3 into j omega plus 4. So this is a j omega plus 4. So from this expression, we can solve, we can apply the partial fraction concept here. Here apply the partial fraction concept, because we need to find small y of t. We have to separate this equation through the partial fraction concept. So what is the, already we know that partial fraction concept, that is 1 divided by j omega plus 3 into j omega plus 4. That is written as, that is applying the partial fraction concept, a divided by j omega plus 3. Here multiplication comes into plus term once applying the partial fraction concept, b divided by j omega plus 4. Now here we are applying the, we have to find a value and b value using partial fraction concept. So we can take here LCM, this right hand side, that is right hand side, that is a into j omega plus 4, j omega plus 4 plus b into j omega plus 3 plus 3 divided by this numerator, that is this term, that is j omega plus 3 into j omega plus 4, j omega plus 4. So these terms comes like this, that is we can take LCM here. After taking LCM, our terms comes like this, a into j omega plus 4 b plus b into j omega plus 3 divided by j omega plus 3 into j omega plus 4. From this concept, we have to find a value and b value. So we now equate this equation and this equation. From this equation, this denominator term will be cancelled. So after cancellation of this denominator, now we can find a value and b value. Here in this j omega value, how can we able to find the a and b value means, in this term here substitute j omega equal to minus 4. Once we can substitute j value equal to minus 4 means, we can get this term is cancelled. This terms comes like b into minus 1, b into minus 1. So once substituting this value here, after simplification, where we can get b value equal to -1. Once we found the value of b, next we find the value of a. So here, how can we find the a value here? Once we want to cancel the b term value. Once we can substitute in j omega equal to -3. -3 plus 3 equal to 0. So this b term will be cancelled. After the substitution j omega equal to 3, we can get a value equal to 1. Once we are getting a value and b value, that value has to substitute in this equation. So from this equation, we can find the answer, that is y of j omega equal to 1 divided by j omega plus 3 minus, here b value equal to, here b value equal to -1. Substitute that value here, that is 1 divided by j omega plus 4. So once we are applying the partial fraction expansion, we can convert it into capital Y of j omega equal to like this. After this, we want to take inverse Fourier transform using standard pairs. Already we know that if in the inverse Fourier transform for 1 divided by a plus j omega equal to e power minus at into u of t. Using the standard form equation, we can simplify the y of t. That means there is 1 divided by j omega plus 3 written as e power minus 3 into u of t. Then this term, that is -1 divided by j omega plus 4, written as minus e power minus 40 into u of t. This is the output response of given system. So through this concept, we can simplify the output response of the system. This is the overall final answers of given system. That is frequency response equal to capital H of j omega equal to 1 divided by j omega plus 3. Then output spectrum, that is capital Y of j omega equal to 1 divided by j omega plus 3 into j omega plus 4. After this, we can simplify the output signal, that is y of t equal to e power minus 3t minus e power minus 4t into u of t. Thank you.